Hi, I'm Brad,
I'm Zach.
and for our project, we decided to do a deep learning-based algorithm acceleration for license plate detection and recognition. Just a little background on the problem. There are some conventional methods for solving this problem, such as clustering and edge detection for detecting characters or even histograms of oriented gradients. However, we decided to go with a deep learning-based approach to leverage recent advancements in CNNs and RNNs.
Yeah, so recent advancements in convolutional neural nets, or CNNs, have allowed us to extract all the relevant features from images without needing extensive feature engineering or hand engineering of features from images themselves. So this makes object detection problems much simpler because the CNN has the capacity to learn it directly from the image. Similarly, RNNs have led to a lot of advancements in character recognition because their ability to learn temporal relations, and this is very useful for sequences such as text sequences. So two main approaches to reading characters such as license plate sequences are actually segmenting each character in the sequence and then doing recognition on each of those individually. And then a more recent approach uses this loss function called CTC loss, which allows the network to look at an entire image all at once and perform character recognition without doing the segmentation. So this will tell it where in the horizontal image plane the activations are the most probable for each character, and then you can do character recognition from there. So we saw in literature that there are two main approaches to solving automatic license plate recognition. There was one-stage approaches and two-stage approaches. So we actually tried to implement both of them and see which one worked the best. So the one-stage approach involves passing an image into one large network that does both detection and recognition, sums their losses for multitask learning, and then outputs a final plate sequence. The two-stage approach is actually splitting these apart into separate networks and not summing their losses. So this would involve passing an image into a detector network to detect the license plate, taking a crop of that license plate from the detector network, and then running a character recognition network on that, and then returning a plate sequence. So you can see here we'd have one large network trained to optimize both recognition and detection loss, and then the two-stage method would be optimizing them each individually. So our approach for the two-stage method was using RetinaNet for the detector. So RetinaNet's based on the ResNet 50 backbone. We can actually use any ResNet backbone, but we chose to use ResNet 50, and then passes the output of ResNet through a feature pyramid to improve the semantics of each feature at different scales. So then each of these features in the feature pyramid are passed through two subnets, a classification subnet and a bounding box subnet. From this, we can simultaneously predict bounding boxes and the classes of the bounding boxes, which is a massive speed performance when compared to other methods such as RCNN, which takes two different passes through the network. And so yeah, that improves the overall speed of this system while also maintaining performance. However, this does add to class imbalance because we do have about a 10,000 to 1 negative classification to positive classification. So this class imbalance would actually hurt performance quite a bit, but they introduced focal loss, which adds a focusing parameter, hyperparameter, which focuses on misclassified examples. So the overwhelming number of misclassified examples won't actually hurt the loss. You'll be able to focus on them, and the ones that are easily predictable will not account for the loss as much as the ones that are hard to predict. So after the image passes through the detector, we get a set of bounding boxes with classification, with classes. So every class that's positive for license plate, we can take that bounding box, crop the image, and then run that cropped image through an OCR model. So for the OCR model, we chose CRNN because this performs at state of the art for character recognition. And CRNN involves a convolutional neural network then passed into a 2-layer bidirectional recurrent neural network. In our case, we use an LSTM. And then the output of this is run through a CTC loss, which, as we described earlier, allows us to do sequence-wide recognition without the need for individual character segmentation. So the other method that we proposed and implemented was the one-stage approach, which combined the two methods we described earlier into a single network and trained them using a multitask loss. So as you can see in this diagram here, we have an input image, goes to ResNet 50 as before, goes into your feature pyramids, and then from each of the feature pyramid layers, we get a regression subnet and a classification subnet. But rather than these being outputted right into the post-processing layer where non-max suppression is run and we get our final bounding boxes and scores, we pass these straight into CRNN. So the features, the image, the bounding box and class outputted by the subnets will be passed into CRNN. We'll run convolution on those crops and then pass into the bidirectional RNN as before, run CTC loss, and then we'll do all our post-processing. And then the final output will be the sum of the loss of RetinaNet and CRNN. So this would be L1 loss of bounding box regression plus the focal loss for classification plus CTC loss for character recognition. So all of these will be summed and optimized so we can jointly optimize this entire process. And the intuition behind why we want to jointly optimize these is because the performance of one is highly dependent on the performance of the other. For example, if RetinaNet performs horribly at predicting bounding boxes, then CRNN doesn't have a very good chance at doing a good job. So the loss of RetinaNet should be accounted for in the loss of CRNN for character recognition. So summing losses should improve the overall system. So the results are as follows. We were able to get an 88% precision on RetinaNet for license plate detection. The inference time on my CPU, which is a 15-inch MacBook Pro, was 174 milliseconds. And this was using the AOLP dataset. And they actually gave the inverse train test split. So they gave 1749 test set and 300 image train set, but they were using more classic computer vision methods. So this train test split didn't make sense for us because we needed more data to train on because of deep learning. So we actually inverted the training test split, and so these precision metrics are reported on the test set, the 300 image test set. So then after that, the CRNN model performed pretty well. It gave us about 81% test set accuracy. And we were fairly pleased with this, but then when we ran it as an entire pipeline running license plate detection and then character recognition, we ended up with a 40% end-to-end test accuracy, which was not very good. So this surprised us, and so we empirically looked at what was happening, and RetinaNet was doing a great job at predicting license plate bounding boxes, but CRNN, for some reason, stopped working very well. So our intuition here was that CRNN was trained on perfect bounding boxes from the ground truth labels of where a license plate was in the images. So we figured that RetinaNet was outputting, slightly imperfect bounding boxes, maybe shifted a little bit, maybe a little bit too large, a little too small, and CRNN wasn't able to generalize to these new bounding boxes. So what we did was we added image augmentations. So we retrained CRNN, but this time we did random shifts in the license plate crops. We did slight rotations. We added Gaussian noise to the image. So we did all these augmentations to help CRNN generalize. So we retrained it with these. We maintained similar tested accuracy with CRNN alone, which is about 80%, 81%. And then pipeline actually increased by 20% up to 61% test accuracy. So this seemed to work. 61% isn't great, but clearly the problem is isolated in the character recognition. So perhaps training on more data, adding more aggressive data augmentation, and tuning the hyperparameters of CRNN would improve the performance quite a bit of the end-to-end method here. And then for the one-stage method, this actually became very complex to train. We had to implement it from scratch, and training took much longer. We actually couldn't get it to converge, and the loss function was very spiky. So for the longest we trained it for was a couple hours, and it was only able to perform at 43% end-to-end accuracy. So not great. It was about as good as the two-stage method without augmentations. And our intuition here is that we added a lot of layers. You know, RetinaNet was 50 layers plus all of the subnets. So that was quite large. And then we added 7 layers of convolution, and then 2 recurrent neural network layers with 256 units each, and then the linear layer on top of that. So overall, we had a lot of parameters we were trying to optimize with one loss optimization step. So I think perhaps if we chose a simpler method, maybe fewer convolution layers, and use the simpler detection model than RetinaNet, this would have been easier to optimize and perhaps given us better results. And we saw this in literature afterwards, that people generally went with simpler methods. But we thought RetinaNet would outperform these methods, but it turned out to be very difficult to optimize. So we ended up sticking with the two-stage method for the rest of this report because it performed much better than the one-stage method.
Now that Zach has discussed our overall approach and implementation of the project, I'll discuss the network compression aspect. So we decided to compress CRNN through quantization and pruning. Quantization is the act of moving from a higher precision representation, such as 32-bit floating point, to a lower precision one, in our case, 8-bit fixed point. So as we saw in project 2, this actually increased the accuracy of our model, which we were testing to the regularization effect that moving to a lower precision representation provides. Essentially, it is undoing the overfitting that arose during training. This compressed our network by 4 times. And you can see the results of our quantization in the top right, where iteration 0 represents before any quantization took place. 1 is our first round of quantization, and then 2 is after training and quantizing again. We can see that the accuracy didn't improve much, so we decided to stop after 2 iterations. Next up, we have network pruning. So we were actually surprised to see that our network was very sensitive to pruning. In the bottom of table 5, you can see that our accuracy dropped by almost 11% after just compressing the network by 8%. So we believe that the network is at its full capacity, and thus, given it only has 7 convolutional layers, and thus pruning weights removes actually some important connections. We believe that a network such as ResNet or RetinaNet with its 50-layer backbone would perform much better under pruning. And also you can see that we didn't prune any parameters from the recurrent layers. Just empirically, we saw that this reduced accuracy by a lot, so we decided to avoid that. Next up, we have the FPGA implementation. This is the complexity evaluation package that was provided to us. This is the output of running the evaluation on the CRNN graph. We can see towards the bottom, we have each layer and its simulated latency. Overall, the simulated runtime was about 3.35 milliseconds and a very impressive 298 frames per second. Next up, we have a screenshot of the profiling tool we used for our network. This is showing the profiling of the fifth convolutional layer, and we see it takes around 0.62 milliseconds. And on the next slide, we have a table of latency for each layer. Overall, we can see there was only an 8.8% speed up. Personally, we were slightly underwhelmed by the speed up. However, we can attest this to not only TensorFlow's optimizations, but also the fact that we were running this on a GPU.
Yeah, so in future work, we'd like to train these on more data. Obviously, more data in deep learning is always going to improve performance. Our data sets were only about 1,700 images, so increasing that is definitely going to improve performance because that's at the very smallest end of the spectrum in terms of deep learning data sets. And then as our results showed, we should probably focus more on the OCR model. CRNN was definitely the performance bottleneck here. RetinaNet empirically performed very well, and then when we combined it with CRNN for the end-to-end model, CRNN could not perform very well, even though RetinaNet gave it very clear bounding boxes. So as I said before, adding more image augmentation, tuning the hyperparameters, and then tweaking the architecture of CRNN, particularly in the CNN layers, might give us better performance. And then also, again, as I mentioned earlier, trying a simpler end-to-end model, this one stage method, might perform better. And we saw this in literature. They had 4 convolution layers to do the detection, and then they added 7 convolution layers to do all the recognition, and then a recurrent neural net at the end of all that. But that is substantially smaller than our network, our one-stage network. So we thought that making it deeper and larger and more sophisticated would just improve performance, but ended up making it very difficult to train, very difficult to optimize. So in future work, we might want to experiment with simpler methods, such as they did in those works. And all references are cited in our paper we published, and any references not in that paper are actually cited in these slides. So thank you.